Well, happy Friday, everybody. Woohoo! Yeah, you're supposed to say it's Friday. And regardless, we haven't done that in a long time. But as I promised, I'm not there today. And so just hopefully the sub directed you to this video so you can understand what we need to get done this today and this weekend. And then you get out there to get some work done on some stuff. First question for you. Would you rather live under a sky with no stars at night or live under a sky with no clouds during the day? All right, just a few reminders here for today. First of all, lab notebooks are due on Monday. So again, if you have any questions on those over the weekend, send them my way, or questions today, send those questions my way. I can help you out with that for the lab notebooks for Monday. We also have a test coming up on Tuesday. The sub should have given you a review checklist today, along with a couple other handouts. And so make sure that got taken care of. I've also posted an extra practice exam in Schoology that you can use, and that's just completely optional if you want more practice. Last night you had problem set 10G to take care of. Again, answers for that were posted, of course. If you have any questions on anything on 10G, send me a message, okay? And I can put out a video response or something like that along the lines. Okay, so if there's anything on 10G, please send me a message. All right, so today we are going to take some of the things that you learned in last night's POGL, and we're going to summarize those up as we talk about equilibrium work and free energy, and also relating free energy to the equilibrium constant. So again, last night you were to have finished up the POGL on work, equilibrium, and free energy. If you have any questions about that, as always, send me a message. Okay, this set of notes is about equilibrium, work, and free energy. So taking some of the ideas that we learned from the POGL yesterday and expanding on those a bit. There is a set of notes for you in Schoology that you can use or use your own. You know the drill. All right, so first reminder here is that as we talk about how reactions happen, there's always two big camps that we put things into. One is kinetics, which we learned last unit, so talk about mechanisms and rates. And the other one is thermodynamics, okay, which is if a reaction happens, as well as what is the state of energy at the beginning, at the end. So things that fall underneath thermodynamics is equilibrium, okay? What's the equilibrium position at the beginning and at the end? Enthalpy. What is the overall heat transfer that happens during the process from the beginning to the end, the delta H? Spontaneity. Is the process thermodynamically favorable? Okay, that's delta G. And of course, delta S, the entropy, also falls underneath thermodynamics. All right, so a couple things here. First of all, when we talk about equilibrium now, we actually have two different definitions that we can use for equilibrium. One is our standard equilibrium definition, which is when the forward and the reverse reaction rates are equal. In other words, when Q equals K is a way for us to talk about that. And again, the forward rate and the reverse rate are the exact same. Okay. Second definition of equilibrium we have is a situation where the free energy in a reaction system is at a minimum. In other words, delta G equals 0. Okay. If something is at equilibrium, that will be the case. If something is not at equilibrium, it will move back toward either those forward and reverse reaction rates being equal or towards delta G being equal to 0. Okay, we saw this yesterday in the POGL, right? If Q was greater than K, we went back toward equilibrium. If K was less than Q, we went back toward equilibrium. Those were both spontaneous or thermodynamically favorable, all right? And so in both situations, we would once again have a situation where delta G equals 0 is where they end up, less free energy. Okay. So if we then take those definitions of equilibrium and we interpret them a little bit, that then means that if delta G is negative, the forward reaction is thermodynamically favored. Okay, so over here we have delta G is negative. If delta G is positive, the reverse reaction is thermodynamically favored. Okay, These equate with the situations where Q is less than K and Q is greater than K, which then leaves us with the last situation, which is if delta G is 0, the system is at equilibrium, which is also the situation that we have if Q equals K. Thus, what we've come up with then is an idea that relates equilibrium and free energy to one another. Okay? And if we take that then and we start manipulating some equations and come up with a quantitative expression of this relationship, we can find out that we can find the delta G for any reaction under non-standard conditions using this relationship. Delta G equals delta G standard plus RT ln Q. Okay? At standard conditions, all the pressures and concentrations become 1, either 1 molar or 1 atmosphere. And so as a result of that, in an equilibrium expression, Q is going to end up being 1. Again, that says 0 in your notes. Please make sure you change that. So Q equals 1. And if we then take the natural log of Q for the expression, that means natural log of 1 is 0. So that makes this entire term 0. So that would make sense. At standard conditions, delta G equals delta G standard. Okay. But if we're not at standard conditions, if we're at equilibrium, then Q equals K and delta G equals 0 by our definitions of equilibrium. So delta G, we can then sub in, make that 0. Q, we can sub that in and make that K. So that gives us 0 equals delta G standard plus RT ln K. If I rearrange that for delta G, we get delta G equals negative RT ln K. This equation is on our pink sheet. Okay? So then if I go ahead and I rearrange this, right, so it becomes ln K equals delta G naught over negative RT. Okay? If we have that situation then, we can take the exponent of both sides and you get K equals E to the negative delta G over RT, okay, which is the other expression of this equation. This then allows us to figure out the equilibrium constant from if we know the free amount of free energy available as well as the RT. Since delta G is a thermodynamic property, in this particular case, we're going to be using the form of R, which is 8.314 joules per mole Kelvin. All right, so the last piece of this then, if we go ahead and we relate free energy to work, we know that work is one of the ways that energy is transferred. Delta G is free energy, okay? So that's the energy that's available to transfer. So delta G then represents the maximum amount of work that could be done by a process. That's what you need to know about equilibrium, free energy, and work. All right, so let's go ahead and let's do a left side on this. All right, so it says consider the following reaction at 25 degrees Celsius. The values of delta H and delta S are listed there respectively. Calculate the value of K at 25 degrees Celsius. All right, so take a minute and see what you can do with this problem based on what we had in the notes, and then come back here when we're done and I'll work it through. Okay, so how do we approach this problem? I gotta squeeze this up here just a little bit so we can get that taken care of. All right, so I'm going to go ahead and start off with, in order to be able to calculate the equilibrium constant K at a particular temperature, we need to know what delta G naught is, okay? So I'm going to start off with delta G naught equals delta H naught minus T delta S naught, okay, by definition from Gibbs free energy. And so this is negative 58.03 kilojoules per mole, and this minus the temperature, which is 25 degrees Celsius, but we have to add 273 to that, so that becomes 298 K, all right, times delta S, which is negative, and I'm going to right away change those joules to kilojoules, 0.1766 kilojoules per Kelvin. Okay. All right. So we're going to go ahead and work through this and do that math. So that leaves me with a delta G that is negative 5.40. I guess this would have been 298.0 K. And so I get one more sig fig there, 403 kilojoules. All right. So that's what I get in terms of a delta G. Okay, so now we can go ahead and we can figure out the K, and we can use its solved form. K equals E to the negative delta G naught over RT. Okay, but our R is going to be in joules, so I'm going to right away change this to negative 5,403 joules. All right, so if I go ahead and put that in, then I get E to the 5,403 joules over 8.314 joules per mole Kelvin. Okay, and my temperature, joules per mole, and my temperature is 298. Okay, so I'll do that. If I run through and I do that entire math, I get a value of K that is 8.85. And there's my answer. All right, so with that, the very first part of your work here for today is the POGIL assessment. Again, handed that out yesterday, and so you should be able to get that taken care of when you can. That is due for Tuesday in class. All right, so if you don't finish today during class, the POGIL work assessment is due. The notes you just took today, once you added summary and questions to that. We've got problem set 10H, okay, and then we have a set of problems that are sort of like a pre-review, which is entropy and free energy, quick check and study questions. All right, answers for both of these are posted, and that's what you got to work on for the weekend and the rest of today. That's it. Have a good one. And new for 2024, you also have practice problems, AP practice problems. 10D, excuse me, for you to do. Happy hunting.